2, this is the last part of the previous example, part C. I've separated it because it's quite a long solution for the last part. These two took about 15 minutes, but this will take a bit longer. Okay, so let me have a quick look here. So, for this part C, just remember from the previous parts of the question that I naught was equal to 2/3. The other thing which is going to help us is to look at what I3 is. I3 will be 2 times 3, which is 6 over 9 times by I2. Yep, and that's 6 over 9 times, now I2, what will that be? That'll be 4 over 7 multiplied by I1. And that will be equal to 6 over 9 times 4 over 7 times, now what's I1? That'll be 2 over 5, yep, times I0. Now I0 is 2/3, okay? So you can see the pattern here. Stepping down by 2s, stepping down by 2s, okay, and I0 is 2/3 on the end, okay. Now, that's an important thing to realise, because if we're going to show this is to be true, and starting from this expression here, we're going to need to know the pattern. Now, if I was to write that pattern out all the way down, what would it look like? Well, it should step down by 2. So if I found n minus 1, I minus 1, that would be 2 brackets n minus 1 over 2 brackets n minus 1 plus 3, which is 2n minus 2 over 2n minus 2 plus 3 is plus 1. Okay? So if I wrote this down here as I'd have 2n over 2n plus 3 times by 2n minus 2 over 2n plus 1. What did I forget on the end of this? I minus 1. N with n minus 1 here. That'd be I n minus 2 then, wouldn't it? And that's I n minus 2. Okay. So, checking my expressions there. Yes. Alright, so you can see here, this is stepped down by 2 and this is stepped down by 2. So it's consistent with that. So you'll need to know that to write the expansion out properly. Okay? So let's have a look. So if I'm starting with IN, I've got 2n over 2n plus 3. Now we're stepping down by 2's, aren't we? So 2n minus 2 is the next one. And then 2n plus 1. Then 2n minus 4 over 2n minus 1. So we're stepping down by 2's. And we're going to go all the way down to what? We get 6 over 9, 4 over 7, 2 over 5. So it goes all the way down to 6 over 9 times 4 over 7 times 2 over 5. And on the end, it's already ticked up. Here we go. On the end you've got 2/3, which is your I0 here. So the I0 on the end is the 2/3. Okay. Now, we're trying to get some factorials in there, aren't we? Okay, we want to have some factorials. So we're going to have to look at how we're going to do that. Now we can do something with the top line here, for starters. So for the starters, with the top line, I can take out the 2 as a common factor. 2n plus 1. 2n minus 1. And now over here I can have the 2 times 3 over 9 times 2 times 2 over 7 times 2 times 1 over 5. And on the end, I've got my 2/3, which was the I naught. Okay, now just for visualization, I'm just going to replace all the 2's here with red 2's so we can look at them separately. Okay. 2, 2. Okay. That's looking good. Rightio. Now, what do you notice there? We've got n minus 1, n minus 2, all the way down to 3 times 2 times 1. Remember that's I naught there. So I've actually got an n factorial in there, don't I? The other thing to notice is how many terms do I have there? Because that helps me count how many 2's. So if I go from 1 up to n, that's n terms. That means I've got 2 to the n. And n factorial. Yep. Right, all divided by 2n plus 3, 2n plus 1, 2n minus 1. Yep. And that keeps going. Now, what do I get? On the end of that, I put dot, 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 dot. I get 9 times 7 times 5 times 3. And on the top here, if you like, I've got times 2, don't I? Because the 2/3 there. There's the times 2, there's the times 3 from the 2/3. Now, that I can combine the 2 to the n with the 2 to get 2 to the n plus 1, can't I? So I can go 2 to the n plus 1 n factorial. Okay. Now, I do want to get a 2n plus 3 factorial, don't I? So I need to put some extra terms in. So let's see, have a look at that. So 2n plus 3. Now the next term down should be 2n plus 2. But I've got to put a term up here which is 2n plus 2, don't I? I can't just whack something in there without compensating. Now 2n plus 1 is still there, so that's all good. Yep. Now after 2n plus 1 there should be a 2n term. But then I've got to put one up here as well. Yep. And then after that I've got the 2n minus 1 term. Okay, that's all good. Now, how many terms did I end up adding for the working out? Okay, I did one more. So after this one, I would have 2n minus 2. And then up here I've got to put a 2n minus 2 here. Okay? Now, then, right, now what's on the end here? I've got times by, dot, 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 dot. I'm going to have a 9. 7, 5, 3, aren't I? Now I'm going to put spaces in here. 9, 7, 5, 3, space. Okay, because I want factorial, so I'm going to put an 8 here. But that means I'm going to put a times 8 there. Okay, these are all multiplied. Then I'm going to put a 6 here, so I'm going to put a 6 here. Times. Then a 4 here, and a 4 here. Times, times, and then a 2 here, times, and then a 2 here. Okay? Now what I've done then is I've created a factorial on the bottom. Alright? So now, what do I have? I've got 2 to the n plus 1, n factorial. Okay, I'm going to worry about the top line in a minute. My main mission is to sort this out. This will be 2n plus 3 factorial. So the whole denominator now is simplified. It's 2n plus 3 factorial, which is what I wanted. Okay? Now, I've got the n factorial, don't I? I've got the power of n plus 1, which is looking good. I want that to be a 4 though. And the next thing I need is n plus 1 factorial. What I can do is take out the 2's here as a common factor, so 2 outside of n plus 1, and 2 times n, obviously, times 2 outside of n minus 1, and times, is that correct? 2n, yes. Yep. Alright, so then I've got times, okay, dot, dot, dot. That's correct. And then I've got 4, did I have those 4s up there? Okay, so I'm going to have 2. I should have, okay, so I've just realised, almost made it without making a mistake. Okay, that's 8642, but obviously there's other terms in between, isn't there? So that's da 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 da. 8 times 6 times 4 times 2. That's better. Okay. So then I'm going to have 2 times 4, which is the 8, times 2 times 3, which is the 6, times 2 times 2, which is the 4, times 2. So a lot of 2's there. Let's count them up. So I'll put this as a 2, as a 2, as a 2. I'll colour all the 2's differently, so we can see those separately. 2, 2. Okay. Alright, so what we want to do is we want to look at how many 2's we've got. Yep. And I'll colour this as a 2 as well. And that'll be 2 times 1. Okay. Now, count all the way up from 1 up to n plus 1. So if you look at here, I've got n plus 1 terms. Alright? So, that's good. Because, when I come over here now, what can I do? I could say, I've got on the top line 2 to the n plus 1, n factorial. Now how many 2's do I have? I've got n plus 1 of them. So 2 to the n plus 1. And then look, n plus 1, n minus 1, 4, 3, 2, 1. It's n plus 1 factorial, isn't it? So n plus 1 factorial, all divided by 2n plus 3 factorial. 2n plus 3 factorial, which equals, now, 2 to the n plus 1 and 2 to the n plus 1 multiplied together, right, that's going to give me 2, I'm just trying to think of the easiest way to do this, yeah, 2 to the 2 lots of n plus 1, isn't it? 2 lots of n plus 1, yep, then I've still got the n factorial and the n plus 1 factorial. On the bottom I've got 2n plus 3 factorial. Now, how could I'm almost there. Let me rub this bit out here. Okay, the last bit. Alright, so I can write this as 2 squared to the power of n plus 1. I have to rub out this bit as well. Yep. N factorial outside of n plus 1 factorial all over 2n plus 3 factorial, which equals, now 2 squared is 4, isn't it? So I get 4 to the n plus 1, n factorial, n plus 1 factorial, all divided by 2n plus 3 factorial. Okay, that's it. All done. Alright, that's quite a difficult question. Make sure you've got all the notes down, and it'd even be worthwhile trying to attempt that question on your own without looking at your notes. Okay? Alright, that's recursion formula done.